Hello everyone. So I think it's about time we can start with our meetup. So good afternoon, good evening, in fact, good morning to everyone, depending on where you're joining us from right now. So my name is Deborah Doma Kandobala, and I'm pleased to be the moderator for today's event. So before I jump into what today's agenda is going to look like, I want to first of all welcome all of you to our meetup, and we're really happy that you had time or you made time to join us. So let me just speak a little bit about NeurIPS as well. So basically, NeurIPS, for people who are unfamiliar with it, stands for Neural Information Processing System. And it's one of the machine learning and computational neuroscience conference that is held every year in December. But due to COVID this year, the conference has been moved virtually. And the conference actually features invited talks as well as oral and poster presentations of preferred papers by members of machine learning and computational neuroscience communities worldwide. And it also gives access to diverse group of people from all over the world to come together to share and discuss ideas in the domain of artificial intelligence. So the question that remains unanswered is, but why the local meetup? So the local meetup was something that was started last year by the organizers of NeurIPS. They thought it wise that most people are unable to travel down to wherever the conference is taking place, most often in Canada, due to probably visa issues, health-related issues, and many other things. So they thought about introducing the concept of local meetups so that they can make the conference accessible to people all over the world. And that's how come the local meetup was started. And we are really excited to be the organizers for the Ghana local meetup this year. So the proposed workshop for the Ghana Meetup is machine learning for developing countries. So just to touch on that, we are leveraging on the conference videos of the machine learning for developing countries workshop taking part, which is part of the NeurIPS conference itself. So the organizers and partners for the NeurIPS 2020 Ghana local meetup are, so we have Richard Nilante Lawson and Elisha Seno from the Artificial Intelligence and Machine Learning Camp. We also have Asada Adai Dese, Salome Ose, and of course myself, who are from the Accra Women in Machine Learning and Data Science community. And finally, we have Emmanuel Owusi Ahenkai, who is from the African Masters in Machine Intelligence. So these are the people who are the organizers for today's event. And we're fortunate to have some partners as well. So we have the Ghana NLP group. So if you don't know what NLP stands for, basically natural language processing. So we have the Ghana NLP group, Academic City University, Python Ghana, AiGhana, and of course the Artificial Intelligence and Machine Learning Camp in Ghana as well. A keynote talk from Dr. Paul Azunre, and then we would have a Q&A session from him as well. So listen attentively to the talk so you can ask him questions related to his talk as well as Ghana NLP, because he's the founder of the Ghana NLP group. We're going to host 3 invited talks. The first talk would be on using search data to inform public health in Africa. And then we would have a second invited talk, Earth Observations in Machine Learning for Agricultural Development. And then finally, we would have a talk on Colombian mining monitoring, detecting illegal mines using satellite data and machine learning. So the day is fully packed. Just get prepared to listen to very interesting talks. So this basically is going to be our agenda for today, and I hope that you enjoy the event. So I would want to do the honor of introducing our keynote speaker for today. So our keynote speaker is Dr. Paul Azunre, which I already mentioned. So Dr. Paul Azunre holds a PhD in computer science from MIT and has served as a principal investigator on several DARPA research programs. He founded Algorin, a research lab dedicated to advancing AI and machine learning and identifying scenarios where they can have a significant social impact. Paul also co-founded NLP Ghana, an open source initiative focused on using NLP and transfer learning with Ghanaian and other low resource languages. He frequently contributes to peer-reviewed journals and has served as a program committee member at some ICML workshops in AutoML and NLP. He is the author of Transfer Learning for NLP, book which was recently published by Manning Publications. So without much ado, help me welcome Dr. Paul Azunre. Thank you very much for honoring our invitation.
Thank you for having me and for all the nice words. I hope to make your time here today worthwhile. So let me quickly share. I hope everyone's doing well in this crazy time.
Yes.
All right. I hope my screen is visible. Someone confirm that for me.
You're all good.
You see the slides?
Okay, so
No slides.
No slides. Okay.
no slides,
Okay.
yes.
Let's see. Do you see it now?
Yeah, we can see now.
Yes.
Yeah. All right. So today we are going to be talking about putting Ghanaian languages on the global machine learning map. And this is basically work that I do as part of NLP Ghana and Algorin research. So one of them is an open source organization. The other one is like a startup. So both the kind of like the private and nonprofit efforts that are focused on the same goal. So of course, a very easy way to motivate the work that I do is just look at things that don't exist, or some gaps in tools, and a good proxy for that is Google Translate. If you open it up and you look at the list of languages that are in it, the first thing, and you play with it, the first thing you're going to find is that for African languages, or a lot of low resource languages, they call them, the performance isn't going to be very good. And secondly, you're going to find that there are no Ghanaian languages anywhere on this list, right? And why is this important? Well, I mean, it's probably easier coming up with or harder coming up with examples of where it is not used than where it's used. So it can help save lives, right? If people who are deployed to remote areas can talk to the people they have to help, right? And if they don't speak their language, right? This kind of thing helps to save lives, literally. Helps to alleviate poverty, right? Education, digitization, preserving our culture, right? Because everything is now on the internet, and everything is basically what the search engines can understand. Otherwise, it doesn't exist, right? So very soon, if we don't put our languages in all of these platforms, and our our fingerprint in other ways, then we basically not exist, right? So we have to get this done. So this popular meme that goes around, how it started versus how it's going. So we are going to start with how it started, right? How this idea for all of this stuff actually started a year ago at NeurIPS 2019. I thought I would bring that up. And basically, if you just go and walk through, the poster session, you will see a lot of languages being, developed. You'll see Ethiopian languages talked about. Now you're beginning to see Nigerian languages, a lot of work on that. you are not going to see any Ghanaian languages being addressed. And so when I saw this, I thought, I had to do something about it. At the time, I was writing this book on transfer learning for natural language processing, and I felt like, and which is exactly how you do a lot of these things. So I felt like it was a responsibility to do something about it. Immediately, I raised it to, the community of some Ghanaian researchers and linguists and stuff. It took off because a lot of people have been thinking about this, right? So this is how GhanaNLP came about, and basically we try to contribute to developing some data, right? That's how you have to train all these things on data, good data. It doesn't exist for our languages. This is why there are no tools for our languages. So that's where everything starts. We are doing some contributions like that. We're developing computational methods, and most importantly, trying to kind of build an ecosystem of, where we are sharing skills and experience and building it up so that our capacity as a community builds up in this space. And I mean, there are people helping us, right? Like Microsoft gave us some credits to use in the cloud. And, there are more than 80 people in the group. These are the key kind of like contact points if you want to get anything done. We do things, we do research, we do communication, outreach to communities, and our research is split into supervised, unsupervised, and quality, as well as data collection, of course. Now, if you're going to look at all the work being done in this space, it's not just us, of course, and this is important to mention. Masakani, as you can see, there's a icon here. Probably the biggest name now at the continental level. They are driving the development of African languages across the board. And so we've been actually working, and some of our members are members of this group as well. And all of this, all these entities are giving money. So this is a very rich research area right now. For those who are looking to learn something new, I really encourage this. I've never seen anything like it. So if you're looking for something new, okay, so what's natural language processing? Let's get into the science a bit. Natural language processing is basically how do you make computers understand what we are saying and what we are writing, right? That's all it is. So how does the computer understand? And of course, in order to achieve that, you have to convert what we are saying, what we are writing into numbers, because the computer doesn't understand anything else, right? So converting speech into numbers so that and manipulating it with the computer, natural language processing. Okay. These are sort of the kind of things we are doing in the space, or you can divide our efforts into. So data collection, embeddings, embeddings are the numerical representations I just mentioned. That representation has to have the right set of properties. Okay, there are various different ones of them. So we're building them. The translation algorithms, and very important, the last column, CASA API, which is like a library, a Python library that anyone can just download and then run a lot of these methods. We are only starting, but at the end of the day, everything that we are building has to be open sourced and easily accessible to everyone. That's important. So let's look at the neural machine translator a bit closer. I'm gonna try and play this video. I don't know if it will work. So if it's not working, please someone. I'm going to show, we actually have an Android app that we are putting out that showcases the translator that we have built. The Android app is currently under review by the Google Play Store. So as soon as that happens, you'll be able to use it. So this is just a demo of it. I hope you're getting the sound.
No, I'm not sure there is any sound.
There's no sound, okay. But is there,
yes.
You can see the Okay, so I'm here. This is an example of a. Okay. Okay, so I hope you saw that there, there are 4 languages supported, so you can translate between English and any one of 3 Ghanaian languages at the moment: Ga, Twi, and Ewe. And you can use it together with the Kasahara app. You probably know about it already, which allows you to type in the local language. And so you can translate to and from the local language. So you can use these tools together. And then, also we have a web app, and I'll share the link at the end of the presentation. Okay, so we have a translator. It works. Let's just say that. And then, okay, and the translator is it's a neural network called the transformer, which is all the rage right now. All the models that you hear about in the news, like GPT-3, BERT, they're all transformers. This is also a transformer. It's an encoder-decoder transformer, so the classical one. Beyond that, I'm not going to get into much of the details due to the format of the talk, but we have discussed a lot of these things on Medium. We're on Medium, and we blog about it, and we also will publish it in more detail shortly. We're preparing the papers. So now I want to say 1 or 2 words about the representation methods we're working on. So the numerical representation for text and speech. So word embeddings, right? That's the first. The concept of word embeddings is how do you convert, the words into vectors that have the right properties, and these are some visualizations of that. We built one for Twi. I'm showing the actual visualization of our embedding. It's on Kaggle. Even you can hit. You can go to the cloud and just click run and run all of our stuff on Kaggle. So this is an example of word-to-vec embedding we built. And this looking at it a little closer, if you look at this word mami over here, it's very close to a word like papa and mawofo. So this is showing the property that when words are have similar meanings or contexts, they have to appear close to each other in this numerical representation that you build. And so this is showing that it's kind of working in that sense. So this is the word-to-vec. But then we have to build this other model called AiGhana, which is an acronym for a BERT model, now in Akan. BERT allows you to build a better representation because it's able to disambiguate different contexts. And I'll say something about that in a second. But this model, AiGhana, you can use it. We've already open sourced it, and you can use it using this Hugging Face library. That if you haven't heard about, please learn about Hugging Face library. It has a lot of very useful things in it, and we're also using it a lot in our work. So we just 3 lines of code. You can call it. You can you can create the numbers for your words or your sentences, and you can use that in whatever way you want, like cybersecurity, or you want to classify reviews of products on a website, anything like that. You can use this for. Now you can do this in Twi as well. So why did we already did word-to-vec, so why do we need AiGhana? Well, if you look at these 2 words at the top, 2 sentences at the top, he examined the cell under the microscope, and he was locked in a cell. There are the same word cell is used in 2 different ways with 2 different meanings, right? In the first case, we are talking about biology. In the second case, we are talking about somebody getting arrested and put in jail, right? Something completely different. So it turns out that word-to-vec cannot distinguish these 2 different meanings. And so it always assigns the same numbers to both of these uses of the word cell, which is not that very good, right? We can do better than that. And so Abna is able to distinguish between these two different contexts. And the way it does it is it looks around basically each of these target words and tries to determine from the words around it what it might mean. That's the way to say it. And like a tree example here, the word so in these two sentences means two different things: big and on, right? Two different things. So Abna is able to catch that, whereas Wetvek cannot. So this is why we needed it. And yes, and we are working on building this API now. And I guess before I conclude and open up for questions if there's time, it's very important, I guess, for anyone working in this space to think about the ethics of what we're doing. So you may have heard some of these examples, like how say computer vision systems can be racist in a way because they're not accurate for dark-skinned individuals, or they assign dark-skinned individuals into criminal groups, right? In use in law enforcement. It's very important that when we use and we build this kind of tools, that we think about ways in which it could go wrong, and that we give very clear caveats for the way our technology is used. And I'm not perfect at it. I'm not an ethicist, but I'm trying to think about it. And I also try to encourage anyone to do the same. It's very important. Without going through this kind of process, I don't think we should be releasing very powerful tools, right? So GPT-3, for instance, has been shown to like basically have learned all the toxicity on the internet, the sexism, and so sometimes you may if you build a text generating tool on GPT-3, it might return some really offensive stuff. So you got to take that into account. So if you want to join us, please go to this. If anything of this like this is interesting to you, please join us, and we're happy to work with more people. Share our knowledge. Maybe you can teach us something. So GhanaNLP.org/join us. Just send an email to this email address. That's another way to do it. All of our social media, if you like that. Yeah.
Okay, that was really a great talk from Dr. Paul. I really enjoyed everything. So we want to move straight away to the next talk. So the next talk is titled Using Search Data to Inform Public Health in Africa. And the speaker is Dr. Elaine Nsoesie. So a brief profile about our speaker. So Dr. Nsoesie is an assistant professor of global health at Boston University School of Public Health. She has a PhD in computational epidemiology from the Genetics, Bioinformatics, and Computational Biology program at Virginia Tech. She also has an MSc in statistics and a BSc in mathematics. Her research is focused on the use of digital data and technology to improve health in communities globally. Her work has also focused on addressing bias in digital data and understanding factors influencing disparities in health outcomes. Her research findings have been reported in major news outlets and science magazines, including Science, Smithsonian Magazine, Scientific American, Washington Post, NPR, and the BBC. She's also on the advisory board of Data Science Africa and Data Science Nigeria. She's also the founder of RETHE, an initiative focused on providing scientific writing tools and resources to student communities in Africa in order to increase the representation in scientific publications. She has written for NPR, The Conversation, Public Health Post, and Think Global Health. Dr. Nsoesie was born and raised in Cameroon. So welcome, Dr. Nsoesie, for our next talk. Enjoy it.
My name is Elaine Nsoesie. I am an assistant professor in the Department of Global Health at Boston University School of Public Health. And today I'm going to talk to you about using search data to inform public health in Africa. A lot of the work I do falls under what's called digital epidemiology. So if you think of epidemiology as a study of the patterns of disease, injury, and health, and drivers of these patterns in specific populations, then digital epidemiology is the same thing, but we tend to focus on using non-traditional data sources. And these include things like mobile phone data, call record data specifically. It also includes things like internet data from places like social media or business review websites. And we try to understand how these data sets can inform health in specific populations globally. These data includes text, images, videos, sound, location, biological, etc. So in this slide, you have a few examples of the kinds of information that we might capture on a social media platform. So you have someone talking about the flu, you have another person talking about getting the flu shot. So this information can be useful if we're looking at people's attitudes toward vaccines. It could be the flu vaccine, it could be the COVID vaccine. You can also look at how people talk about weight, how people talk about food, and these can inform us about things like physical activity in different communities. You can inform us about obesity prevalence in different communities. So this data can be very useful, and we've used it for a lot of different purposes. So in my research, for example, I've looked at how we can use search data to understand people's search habits towards things like food locations. So where is the nearest fast food restaurants, or people searching for where locations for gyms, and that can inform us about how people think about physical activity or what kinds of information are available to them in different communities. Most of the work I've done in the Global South has mostly focused on search data, which is why I'm talking about it here today. But I've also looked at how we can use remote sensing data, specifically satellite images, to inform us about disease surveillance in different Latin American countries. And currently I have a few ongoing projects on remote sensing data in Africa. And what I have learned from working in Western countries and working in the Global South is that when it comes to the adoption of digital platforms in countries, specifically in sub-Saharan Africa, we have to really think about the challenges that are unique to this context, and we have to develop solutions that are specific to that context. So that means thinking about the cultural, the social, political aspects of different countries and different cities, where we want to make sure that we're not just assuming that what applies in one location is going to apply in another. I want to start off with this paper because it's one of the first papers that looked at such data comprehensively across the continent of Africa. It's definitely worth reading if you're interested in how we're using non-traditional data sets or non-traditional data sources for public health surveillance in Africa. And the focus of this paper was to understand health information needs in Africa. And they looked at searches related to malaria, TB, and HIV/AIDS. And these was very informative because you could see where searches were coming from, you could see where areas where there wasn't a lot of data, and you can see what people are searching for. So what kinds of information do people want to know, or want to find, what kind of questions people have, and they're trying to find answers to. We did a similar study during the COVID pandemic, which is still ongoing, to understand what kinds of information people were seeking in 21 African countries. So on the right, where you have the figure, you can see the different questions that people are asking, and these questions have changed over time. So people ask questions about, like, coronavirus, how the coronavirus infects different people, coronavirus on surfaces, whether you can get infected by maybe touching a particular type of surface, the nature of the coronavirus, whether it's similar or different from the flu and other infectious diseases, and then you have questions about symptoms, which people are still asking up to today. And what we found when we looked at this data was that questions changed over time. So at the beginning of the pandemic, many people were asking whether the virus was similar to the flu or whether it was similar to other infectious diseases. By the time we were doing this study, we saw that a lot of questions had transitioned to where do I get tested? Do I have to pay for testing? And so this is very important when you think about developing public health resources for people. So if we wanted to inform people about where to get tested, you could see where those questions are coming from and can target those interventions to those particular locations. So we can see what are people in a particular city in a particular country asking for, and then educate them about those questions that they're asking. We also went one step further and looked at search data over time. So we looked at time series of searches and wanted to evaluate whether this was useful in modeling COVID cases, specifically in South Africa, where in terms of testing and reporting of cases, it's been the highest across the continent. So we crowdsourced searches. So we wanted to know what people in South Africa were searching for. So we talked to South Africans, asked them about what they were searching for, what their family members were searching for, and came up with a list of terms. So this is just some of the terms. It's not a complete list. You can find the paper online if you're interested, and you will see a complete list of the terms that we search for. So one of the things that I wanted to highlight was the home remedies. So people were searching for home remedies because people were trying to either prevent infection or manage the disease when they actually get infected. And then you have symptoms, of course, and these were the ones that tended to be very significant. So here we have correlations between the search terms and the COVID data. When you look at the most significant correlations, you see that those are things like COVID symptoms, loss of smell, symptoms of COVID, loss of taste. So you have specific symptoms that are significantly correlated, and then you have just general searches for symptoms. So over at the bottom, you have all the provinces. So South Africa has 9 provinces, and we're looking at each province separately. At the top, you also have home remedies. So eucalyptus oil is something that people were using. Zinc is another thing that people were using as well. So those ended up being very significantly correlated. So if you look at trends in COVID cases and you look at trends in searches for these home remedies, you will see very high correlations in temporal trends. But this differed for the different provinces, as you saw in the figure. And so we created separate models for each of the different provinces. So we use elastic net regression, very simple, and try to see if we could estimate the proportion of positive cases given the search data. And so on one side, you have a model estimates a proportion of positive cases, and then you have the confidence intervals around that. On the other side, you just have the line plot. So we have the date, and then you have the proportion of positive cases, and then you have the cases, and then you have the model. And then the black line that you see there is the date at which we stopped the model fitting. So we fit the model from the beginning from the start of the pandemic in South Africa, or epidemic in South Africa, up to that time point. And then after that, we're predicting one step ahead. So we're saying that given that we're seeing information given that we've seen searches at time point t, can we predict what the proportion of positive cases will be at time point t? So the results varied across the different provinces. Some provinces did a lot better than others. And another thing that we found was that if we said, okay, let's look at the searches at time point t and predict cases at time point t plus 1. So we're basically predicting into the future. What we found was that several of the models did much better. And the possible reason for this is that people get infected they have symptoms, excuse me, you don't immediately go to the hospital. So they might take several days, they might even take a week to see how their symptoms progress before they get tested. Or they might get exposed and start Googling, trying to figure out what the symptoms are, but get tested until much later on. And so this is being captured in our models, where you see that if we're looking at searches at the current time period and then trying to predict in the future, we do much better for some provinces than when we're trying to predict at the current time point. Again, as I mentioned, some provinces did much better than others. And one of the reasons is that the search data drives the model. And for some provinces, we don't have very good search data. The volume of searches is very low. And there could be many reasons why this is happening. It could be issues around internet access in some provinces. It could have to do with socioeconomic factors. It could also have to do with information that people have about the virus. So if you already know what the symptoms are, maybe you're less likely to search for those symptoms. We did a similar study before the COVID study, where we looked at influenza-like illness in Cameroon, using the same idea where we're saying context matters. Let's see what people would search in this particular context if they were looking for flu-like information, for information about influenza-like illnesses. Again, we crowdsourced possible searches from people from Cameroon and from Nigeria as well, since there's some cultural similarities there. We wanted to know, like, what would your aunt search for if she had flu-like symptoms? And then we put together those terms and extracted that from Google for those searches across multiple years, so from 2012 to 2018, and then developed models. So if you can see the figure on the right, you have support vector machine, random forest, multivariable regression, and then AR is autoregressive regression. So we're saying that given what we've seen in the past, we want to predict what we'll see in the future. And we did these different versions of this model. And for one, we just use saying we've seen influenza-like illness in the past, let's predict what's in the future. In other models, we say we have influenza-like illness in the past, but we also want to add another variable like time. And in another case where you have the 2 weeks, we're saying we want to look at the last 2 weeks of influenza-like illness reporting to predict what we will see in the future. And similar to what we have in South Africa, we saw that home remedies or traditional remedies were very significant in our models. We also saw searches for things like AIDS and malaria and TB. So these are high burden infectious diseases in Cameroon and several countries in South Africa, in several countries in Sub-Saharan Africa. And so people know about these diseases and they're likely to search for them. So if someone starts having flu-like symptoms, they might want to know if their symptoms have to do with TB, if they match symptoms to TB, or if they're having fever and body ache, they might want to know if it's related to malaria. So what we found out was that by looking at the specific context, we're able to develop better infectious disease models for predicting the trend of influenza-like illnesses, but also COVID-19 in South Africa over time. In addition to infectious diseases, we've also looked at chronic diseases as well. The African population continues to grow. More people are living in urban areas, and more people are going to be living in urban areas in the future. And what usually happens in many urban areas is that the way people think about food, the kinds of foods people consume, the way people think about physical activity and whether they exercise or not, it can change over time. And so if you look at highly urbanized regions of the world, some of them especially in the West, you have high prevalence of certain kinds of diseases. And we're starting to see that in some African countries. So if you look at this figure right here, you have overweight prevalence and obesity prevalence. And you can see that the highest prevalence are in countries in South Africa and in Northern Africa. And so what we wanted to do in this particular study is to start looking at what are people searching for in relation to what we would consider risk factors for the diseases. So things like physical activity and diet, those are two major risk factors. So are people searching for gyms? Are people searching about specific types of exercises? Are people searching for healthy food options? Are people searching for unhealthy food options? This can inform us about interventions. So if we want to design programs to educate people about healthy eating, about exercising, then we can look at how interest in these topics have changed over time for specific regions, and then develop those interventions to address those issues. So here we have the 4 countries in Africa that have the highest obesity prevalence: Libya, Egypt, South Africa, and Algeria. So if you look at the search terms over time, so you have year and you have search volume, you see that there's a lot of similarity between the North African countries. So Libya, Egypt, and Algeria have gym, yoga, and then there are some slight differences in you have weight here, you have breakfast there, you have exercise there. And then when you start looking at South Africa, you see that it's very different from the other 3 countries. So the terms that were more significantly correlated with obesity prevalence in South Africa were things like how to exercise, green tea, so people use green tea as a diet, weight gain was another search as well. So what this tells us is that context is definitely very important. So it's not just about looking at the continent in general, but how do we look at each country, and how do we even go down to the province level to understand what are the differences at the province level, so that we're developing more targeted interventions and we're not just making assumptions that everyone has access to the same information or everyone is seeking the same types of information online. Again, we used machine learning models, found that random forest was the best model. If we fitted a model to estimate overweight prevalence using all the such data, this is what we get across all the different countries in Africa. The results were very good. And then if you do the same, so this is just the fitted, if we do the same where we're saying we fit part of the data and then predict the other half of the data, this is what we get. So our predictions also were pretty good. So of course, there are challenges when we think about using digital data for surveillance in sub-Saharan Africa specifically, or across Africa. There is a shortage of high quality surveillance data in many countries. So what that means is that if I wanted to develop a model where I say, okay, I'm looking at what people are searching online, how does that relate to what we have on the ground in terms of particular infectious disease or chronic disease, I might not have the data that I need in that situation. And so that limits validation of the data that I'm getting from the internet. And so there is definitely a need for developing better surveillance systems, but also looking at how technology can help supplement what does not exist in terms of public health surveillance. The cultural influences, I don't think this is a challenge per se, but it's important to think about. So cultural influences in sub-Saharan Africa mean that people think about health and talk about health and disease differently. So the methods that we have used in the US, for example, might not apply to many countries in sub-Saharan Africa, so we have to think about that context. What do people feel comfortable talking about? And I think there might be some changes after this pandemic that we'll see in terms of how people discuss disease symptoms online, especially on social media platforms. There are also socioeconomic inequalities that we have to take into account. Not everyone has access to the internet. And if someone has a mobile phone, they might not still be able to afford data to be spending time on Google searching for health-related information. And so that leads to issues around representation. So not everyone is represented. So how do we build systems that take into account the fact that not everyone is represented? How do we target the people that are represented without leaving out the people that are not represented? How do we combine some of these technological approaches with more with non-technology related approaches? How do we combine them to improve health in different communities in Africa? And then your ethical challenges, of course. When people put data on the internet, they're not necessarily expecting that data to be used for research. So, for example, ethical challenges around how we use data definitely affects what we do in terms of research with data from digital sources. So not everyone understands that when they put information on certain platforms is considered public information and can be used for research. So we definitely have to think about how do we develop informed consent especially in cases where we're studying topics that are sensitive like mental health issues. How do we make sure that people understand how their data is being used? In cases where the data is aggregated and people are not you can't identify individuals in the data, that works pretty okay, and that's most of the work I do. But there are definitely opportunities for developing individual health approaches that definitely demand that we think about ethics and we think about how people can be affected negatively by using their data for public health research. Of course, there are ways in which we can address these challenges so that we can use this data to create the kinds of benefits that it has the potential of having in these situations. And there are three that I can think about. One is developing early warning systems for public health crisis response. So by looking at real-time information about public health issues, whether it's disease outbreaks, as the information comes in, we can harvest that information and can develop systems where we're warned earlier about what's happening in different communities and we can respond to that. We can also have fine-grained representation of public health concerns, which will enable us to develop targeted interventions. So, because data is geolocated, especially when people use their mobile phones to search for things or to post things on social media platforms, we can get locations where information is coming from. It could be from a city, it could be from a particular neighborhood or community, and we can use that to develop more targeted interventions. So instead of developing interventions that cover the entire country and assuming that everyone has the same interest, we can look at a particular location that is being that needs that intervention and then develop that intervention for that particular location or community. Lastly, timely feedback on public health policies. I think social media is an amazing place for this where people share their opinions about different things. As new public health policies are implemented in different countries and communities, people respond to that on social media, they respond to that on radio, they respond to that on different platforms online. All of this information can be useful for us to see what does the public understand, what do they not understand about these policies, how can we make improvements so that people can understand better, or how can we change policies that are not working for people. So these are all things that we can do with non-traditional data, especially from digital sources. I would like to acknowledge my collaborators on this study. There's so many of them. These are the ones that appear on these papers. And thank you so much. If you're interested in any of the studies, you can find them on my Google Scholar account. If you don't find anything there, feel free to send me an email. That's my email on the screen.
Okay, so that was another great talk from Dr. Elaine. I guess you all enjoyed it as much as I did. And we'll move to the next invited talk. So the next invited talk is on the topic Earth observations and machine learning for agricultural development. Interesting topic. And the speaker is Dr. Catherine Nakalembe. So a brief profile too about our speaker. Dr. Nakalembe is an assistant research professor at the University of Maryland. She is the NASA Harvest Africa Program Director, a member of the NASA Severe Applied Sciences team, and serves as the Agriculture and Food Security Thematic Lead. She is a 2020 Africa Food Prize Laureate for her dedication to improving the lives of smallholder farmers using satellite technology to harness data to guide agricultural decision-making. Her work in this area has helped prevent potentially disastrous impacts of crop failure. Her relentless efforts have also promoted the formulation of policies and programs that are directly impacting farmers against the impacts of food failure. Dr. Nakalembe was a 2020 UMD Research Excellence Honoree and 2019 was a recipient of the inaugural GEO Individual Excellence Award. She was featured in the 2020 Women and GIS Volume 2 Stars of Spatial Science ESRI Press Book. Dr. Nakalembe grew up in Kampala, Uganda, where she earned a BSc at Makerere University in Environmental Science. She earned an MSc in Geography and Environmental Engineering from Johns Hopkins University and her PhD in Geographical Science at the University of Maryland. Without much ado, welcome Dr. Nakalembe.
A good day to everybody. My name is Catherine Nakalembe. I'm an assistant research professor at the Department of Geographical Sciences at the University of Maryland. And I'm excited to be here today to talk about how we're using Earth observations and machine learning for agricultural development as part of this NeurIPS machine learning for development workshops with a main focus on improving resilience. Just a bit of a backdrop as to why my work focuses on this is for my research, I've been doing remote sensing for agriculture and looking at drought and understanding how Earth observations can be used to improve decisions in agriculture and food security. And the basis of this, of course, is the fact that we have we have many Earth observing satellites that are providing critical information at this time. And the data are timely, objective, repeatable, and offer global scale and a long-term dense record. As well as, recently with advances in methods, it is possible to monitor many diverse landscapes and provide critical information for places where, with traditional methods is hard. And this is forming, critical data that is informing decisions. And I strongly believe that today we can make significantly smarter decisions about how we're managing our planet. However, there are many places that are still lagging behind, and often the free tools or the data and the methods that have been developed have not been used to that level. And so, despite the fact that machine learning has been applied in many domains of earth science, which is relevant for improving and answering some of the most critical questions today, including how we're changing our planet, through land cover and land use classification, understanding climate and soil moisture and understanding and providing updated products as well as timely information on where our crops are and how those crops are doing, estimating how much water is available, the quality of that water, estimating pollution, and monitoring hazards like cyclones and landslides. Is the technology is there, and with it we can measure. Not only can we understand where we, how the planet is how we can monitor the planet's pulse. However, we can also understand and measure progress at both global and local scale in terms of, not only enabling how we're planning and adapting, as well as developing mitigation measures and achieving goals that we set out to ourselves. For example, the Sustainable Development Goals. And my work primarily focuses on there's not a one goal that you can target without addressing all the others, but my work primarily lies under SDG number 2, which is zero hunger. And so, like I mentioned before, the methods that are available now make it possible for us to monitor diverse landscapes. And so, there's no excuse for not having information about every place on Earth, based on where we stand in terms of the science and the data availability. However, every year we're still bombarded and struck by, disaster, in the sense that even though in some places, it is possible and feasible to monitor what's going to happen, a lot of sub-Saharan African countries where my work focuses, every few weeks to months to days faced with one hazard after another, and each one of these hazards can have significant impact on a community, and many might not be able to recover for years to come. And so it's becoming even much more pressing. And so, food security being one of, if not the most pressing issues in many of these countries. However, when you combine all these hazards and external threats and everything from droughts, extreme flooding, landslides, it becomes incredibly challenging. And in 2019, for example, just looking at sub-Saharan Africa, and this is just a few of some of the events that happened before COVID, which was preceded by, multiple cyclones, the arrival of a desert locust invasion, which has been coined a 1 in 70-year event for Kenya, going backwards from landslides to flooding and this crop failure. So you have a drought, cyclones, flooding, all these extreme events, and then COVID-19 hit. And so you find that in these places where so many million people were already, at risk of food insecurity or already food insecure, these, massive events are impacting their livelihoods even more. And COVID-19, to add, is making it, that its impact on this community is disproportionate, and more people are projected to be food insecure after 2020, just purely because of COVID-19. And so we're far from SDG 2. First, we don't really know where we stand, because the primary things about how much food is available, where it's available, how it's growing is not fully accessible for a lot of the countries that are at risk of food insecurity in the places where we need to address SDG 2. We don't really know. We have, the projection for 2030 is about 840 million people will be, at risk of food insecurity, and we're getting further away. Just the projection of the added number of people due to COVID-19, as I mentioned before, is just incredibly high. There's more conflict, more refugees, there are more disasters. However, technologically, there with machine learning and cloud computing and and all these digital solutions that have been developed over the last couple of years, there are more solutions, there's more data, there are more tools and more insights that we can use to address these. However, we're still far from achieving this. And so the work that I've been doing is primarily falls under the umbrella of the Global Agriculture Monitoring Initiative, GeoGLAM, and under the NASA Harvest and NASA Severe programs. NASA Harvest is NASA's Agriculture and Food Security program, and the Severe program is a joint NASA and USAID initiative aiming towards improving capacity to use Earth observations in various sectors and works globally. And so to achieve, contribute towards SDG 2, there are a number of things that we prioritize, primarily with our work in Sub-Saharan Africa. And we focused a lot in Eastern Africa, in Kenya, Tanzania, Uganda, and Rwanda, and started working in West Africa. However, we have work that monitors agriculture and food security globally with our partners. And these are some of our priorities over the years. One is improving monitoring and early warning systems that provide actionable data and information on agricultural productivity for food security at multiple scales. This is important because, as I mentioned, we have all those satellites in space, as well as the methods and tools and systems that have been developed over the last 30 years that can help address some of the critical questions of today. And so we want to take advantage of these and make them relevant for decision makers. We are trying to advance the methods that underpin the data and systems that inform decisions. And I will talk a little bit about this because it's where machine learning plays some of the most critical roles. We're developing and transferring capacity to national and local users that influence decision making. And so I will briefly touch on that. And our work strength lies in developing strong and long-term sustainable partnerships, because we can't do everything, as well as we can't ensure that something is sustained if we really work in true partnerships. And so in terms of improving monitoring and early warning, we've supported development of the crop monitor systems that have been scaled globally and provide updated near real-time information about how crops are doing, so we can track where there might be serious issues with food insecurity related to a loss in production or a massive event, for example, a drought or huge floods. In terms of priority 2, developing and transferring capacity, we've done this through delivering those systems that I mentioned before that enable countries and organizations to monitor what's happening on the ground. We've done a lot of training, capacity training, and bringing individuals and organizations to be able to use the systems, as well as understand what Earth observations have to offer. We work with experts in the countries and the region who provide not only insights, but technical expertise and enable and bridge the gap with our intended end users. And we're trying to understand the policies and programs that our work can contribute to. These are all important because we can have the best tool or the best technology. However, if it doesn't have a home or it doesn't have a purpose and is not aligned with the goals of the organizations or the individuals we're trying to work with, then it is all lost. And our priority number 4 is developing strong and long-term sustainable partnerships. And we have a lot of partners. Not only do they support leveraging the existing systems, including satellites and data aggregating systems, but they also enable, strengthen, and improve not only the methods and where we're going, but make it possible for end users who might not necessarily, have the resources to take advantage of these maybe high resolution data. We make, that those partnerships make it possible so we can experiment as well as test and deploy things that are relevant for a particular end user. And so going back to priority number 2, which I skipped over because I want to talk about it a little bit more, is we are advancing the methods that underpin the data and systems, and we're doing this in multiple ways, including developing new methods for post-season and in-season classification using deep learning, including using, moderate to high resolution satellites like Landsat, Sentinel-2 and Sentinel-1, combining it with commercially available high resolution data. And we're making this available, we're making our products available to our end user directly, as well as trying to ensure that the methods that we develop can be scaled as well as applied by the end users themselves. And I invite you to attend Dr. Hannah Kerner's presentation in Eyes in the Sky Without Boots on the Ground, which is part of this conference. So you can hear a little bit about what we're doing specifically with machine learning. And in terms of advancing these priorities, particularly for monitoring agriculture in Africa, which is largely a smallholder, this is kind of the backdrop. One of the reasons why we don't know where we stand in a lot of countries, we don't know where crops are, how those crops are doing. It's not only because there are not steps being taken to clearly understand this, but it's quite actually incredibly challenging to monitor smallholder agriculture, which is most cases about 70%, which means that over 70% of populations in a lot of developing countries in sub-Saharan Africa. And so one of the reasons, of course, is that there's low productivity. We have very small fields, they're mixed, and if you're looking at satellite Earth observations that have been available, at least recently it's improved significantly with Sentinel satellites, where we have 10-meter resolution data, as well as with cloud compute. So things have changed rapidly in the last couple of years, and we're able to do a bit more than we did than we're able to do 5 years ago, because we have the compute power to be able to run this huge data sets and provide better insights and better products that are more timely, more accurate. But we still do need to do a lot better. And I'm just going to show some examples of how we're using machine learning in our work, and just show some examples from 2020, where we're combining 2020, of course, you remember, is one of the years where we couldn't do field work. Everybody was locked down, and so we were combining data where we had it, ground data where we had it. So we had labels from the GeoWiki data set, for example, and our partners that have people on the ground who were collecting data, including One Acre Fund and Plant Village. We combined this data, and we got a request from the Togolese government to develop a cropland map, which was needed to advance a program that they wanted to provide farmers with support who were being impacted by COVID-19. And so we combined that with ground data where we have it, where we have extension agents who are working on the ground, for example, in Uganda and in Mali, and using machine learning, as well as some on-screen digitization, we're able to develop rapid maps needed to support the Togolese government initiative. And I invite you to listen in to Gabby Sang's presentation on annual and in-season mapping of cropland at field scale with spruce labels. He will be talking about our work, which I'm just going to touch on a little bit. And so for this particular one, the Togolese government had launched a program to distribute interest-free loans to farmers, providing equipment and supplies through a digital wallet. However, they didn't have good enough record to determine the number of farmers and where those farmers are. And so for this, we developed an LSTM-based model to provide a cropland map using those global data sets that I mentioned, the GeoWiki, as well as where we had data on the ground for Kenya. And then this model has been further extended and developed a crop non-crop classifier and a forecaster for multispectral time series data. So we produced a 10-meter resolution cropland map for Kenya post-season. This is for 2019, and then an in-season for 2020. And we're hoping that we will use this method to generate cropland maps for previous years where we don't have any labels, as well as in other countries where we might not. Why is this data important? Is that if you want to measure how croplands are doing, so if you want to know crop conditions, you need to know where the crops are. However, if you want to understand whether a program is working really well, whether if the intention of the program was to expand agriculture then you could potentially, use these maps to check that. If you're looking at and measuring increase in yield, you would need this, as a basis for your measurements, and this is, why this is incredibly critical. And just to show some impact examples, the capacity and systems that we've leveraged over the last couple of years have led into the establishment of the crop monitor for AMIS, which focuses on monitoring countries that are bigger producers of wheat, maize, corn, and soy. These crops are big food security crops because a lot of the world depends on them for food. And then the crop monitor for early warning, which focuses on countries that are at risk of food insecurity. So we have international agencies, including the World Food Programme and FAO and the Joint Research Commission of the European Union, FuseNet, coming together on a monthly basis and making assessments and producing information about what's going on in these countries. The same approach and method has been scaled as well as adapted to the needs of countries, as well as the regional Eastern Africa crop monitor, which is run by the IGAD Climate Predictions and Applications Center out of Nairobi. And we have one in development for Rwanda. We have a national crop monitor for Kenya, for Uganda, and Tanzania, as well as one in development for Mali. So we've, tried to embed the knowledge and the tools that we have into processes that are useful for the countries on monitoring initiatives. In terms of Togo, which I mentioned before, this information was critical for providing information about where farmers were so that farmers could be, provided with the inputs that they needed in order to overcome some of the challenges posed by COVID-19. Another example, this disaster risk financing program, which relies on one of the systems that I showed before, the global agriculture monitoring and monitoring system, which enables them to do their own assessments to scale this program, which has supported over 300,000 people in Karamoja just since its start, and has realized savings for the Ugandan government that they could, money that they would use for rapid responses in terms of bringing food aid, not spent in when droughts hit. And in summary, weather and climate impacts are getting worse, and they will probably get worse, and more people will be more vulnerable. When you add COVID-19, of course, a lot more people are projected to be food insecure, and so it is really, really incredibly important that we know we know where we stand in terms of where our crops are, what crops are growing, how those crops are performing, how can we improve those crops, and machine learning is combined with satellite Earth observations of providing, a critical basis for answering some of these questions, as well as when, improved upon, can provide critical inputs for providing direct information to farmers. And as climate change progresses, it is going to become even more critical because early warning is better than responding too late. We'll be able to save lives if we're able to forecast and provide critical information earlier than before. And some of the ways to achieve this, so we can have the best models, the best tools, the best satellite systems. However, if national agencies that are in charge and responsible for providing critical life-saving, be it infrastructure or decisions, be it food aid, be it things to improve production, if those things are not delivered on time, then it will be impossible for us to achieve any of the SDGs, because constantly farmers will be on the front lines responding and reacting or trying to manage the situations as they evolve or unfold. Thank you.
That was another powerful and interesting talk from Dr. Nakalembe. Thank you so much for sharing your thoughts and ideas with us. And then we move to the next talk for today, and actually the final talk. The talk is going to be on Colombian mining monitoring, detecting illegal mines using satellite data and machine learning. And this talk would be by Santiago Saavedra. Santiago is assistant professor at the economics department in Universidad del Rosario. He holds a PhD in economics from Stanford University. Last year, he was awarded a Google Artificial Intelligence Impact Challenge grant. His research interests are in development and environmental economics. In particular, he's interested in how economic development affects natural resources and how this in turn affects the path out of poverty. To overcome data availability limitations, he uses spatial and computational tools. He has studied the response of illegal mining to a change in royalty taxes and health effects of global mining in Colombia. Deforestation after the peace agreement and of communal land. He has also studied the migration of miner networks and the labor supply of bike tax in Kenya. Without much ado, help me welcome Santiago for our final talk.
Good morning or good afternoon, depending on where you are located. I'm gonna present you about COMIMO, Colombian Mining Monitoring, that we use to detect illegal mines using satellite data and machine learning. My name is Santiago Saavedra. I'm based at Universidad del Rosario in Bogota, Colombia. And before starting, let me thank the organizers for this great conference. To motivate you, probably you are watching this in your phone or in your computer, and we use minerals. There is like gold and other rare earth minerals in there, and probably they have minerals from illegal mines. It's not a perfect measure, but it is known that in the US, 2/3 of the companies don't know where their minerals are coming from. They might be coming from mines in Colombia, in the Congo, or in India. So maybe just ask that question yourself. Do you know the origin of the minerals on your products? The reason we care about illegal mining is that it affects biodiversity and forests. They create an enormous footprint that is hard to recover for the ecosystem, and they pollute waters, and it gets people downstream, like problems with the mercury in the water. Currently, in Colombia, manual detection takes around 2 years since the time they obtain the satellite image until they release the study announcing where they found evidence of mining activity. What we are proposing here is to use machine learning that will help us analyze in a couple hours the entire country of Colombia, which is the size of California and Texas combined, and generate alerts. So what we are gonna do is not only try to look for the best machine learning model, that's kind of the idea of the conference, but also the idea of this session is how do we use this to like help the government. So I'm gonna divide my presentation in 2 parts. In the first one, I will tell you about the machine learning of behind the scenes, and then I will tell you about the interface, how we plan to communicate to the public our findings. So as I mentioned, for today, I'm only gonna use images of Colombia, but we're looking to expand to the whole world. So if somebody's interested and you have training or testing locations in other countries, we'll be happy to apply the model to other countries. We are using Sentinel-1 and 2, that's I'm gonna be presenting, but in the past we have used Landsat 7 and 8, so we can use more information. And we started like 5 years ago with the data from the 2010 Colombian mining census. And since then, we have expanded to use validations that we can automate. So now we have like a pipeline to continually get more training data. And also we have been collaborating with the government. They have done field operations and they have shared with us the GPS coordinates so we can again keep feeding the model. So here is Colombia in the map in the north corner of South America. And this is the data I have currently of locations that we have validated have mines or that they don't have mines. So we have done from like the United Nations database, which is only detecting mines, to random sampling the whole country. So we can have both strategies. And since then, we did the first batch of predictions and people have been validating this prediction was correct or not. And we keep expanding our data set. And eventually we might cover the whole country, but then we want the model to be accurate through time. What we use, as I mentioned, is Sentinel and Landsat imagery that is hosted in Google Earth Engine. And then we extract them as a TF record. So we use the libraries in TensorFlow, coded in Python, and we use Google Cloud servers to train a bunch of models. We receive artificial intelligence impact challenge for social good from Google that we are really thankful, and that's why we have been developing this project. So this is a little bit what we do. We take the imagery from the sample geometries we have of points we know are mines or not mines, and we divide them in 3 pieces. The first one is the testing data that I haven't touched as of today. That's sacred, is located until I find my best model. And to find my best model, I will do training in 75% of the remaining sample. So, and another 25%. So 25% of the 75% I'm not using for testing will be my validation. So this is what you're going to see today. Based on some training data, how is it looking in the validation data, but I'm not touching yet the testing data. So far, the ResNet 50 is the best architecture we have found, but you will see that we have tried many of them. I will evaluate the model, and then eventually we will do predictions, and that will give me a probability. And then another policy question that is super interesting to think in this session for development is what is the threshold I decide to call something a mine or not a mine? So that's really important because maybe if I have too many false positives, I will lose reputation. Or if it's not only a reputation of the communal platform, is the resources of the government. If they go to the field in costly operations, you might not want to have that many false positives. So that's a balance we will discuss later. This is a little bit sample images that we have from Sentinel-2. So you have the same left and right. I just want to point out that sometimes it's easier to recognize a mine when you don't zoom in too much. So here is the same imagery, but maybe on the right you see more clear which one is a mine and which one is not, that on the left that I added extra zoom, but it's basically all I have to train my model is a bunch of these squares, which are 540 meters side. So we decided it was a good balance between government officials going to the field. So if we give them the center of this square, they probably look around 200 meters. So that's safe enough so that they find the mine. But also you don't want it to make it small enough. That would be better for the government if I'm more precise. But then I'm not taking advantage of the convolutional neural network that will take the information of the neighbors. Before, like 3 years ago, we had a random forest model that was doing pixel by pixel prediction. Now that we switched to a convolutional neural network, you want to take advantage of the neighbors. And we decided that a 540 meters square, which will mean, because the pixels in Sentinel are 10 meters, we basically have 54 by 54 pixels images. This is a little bit of what we have in the validation from Sentinel-2, that's the optical satellite, on the first bi-week of 2020, right? So of course, the idea is to do this every 2 weeks, that we have a new satellite imagery and see what happens. So notice in the bottom that we have of 7,900 squares that I'm using for validation of these images, I only obtain images of 5,800 of them, right? So I'm losing 1,500, and there are some other issues that we have been trying to play with. It's not only the clouds, but sometimes we get these weird stripes on Earth Engine. So we are looking to to find a way of getting rid of these stripes, which seems to be an issue when extracting too many imagery. But if somebody has an idea, that's something we're trying to solve. But at the end, we only get 5,800 out of 7,900 locations that we wanted. That's the imagery of Sentinel-2. And on Sentinel-1, which is the radar, so it can see through the clouds, we get more imagery. We get like 1,000 more, but we still are missing 1,000 images. So we are still trying to understand what happens, because I'm an economist, so I'm not an expert on satellites. Well, I've been learning, but why are we losing 1,000 images? I thought we were going to obtain 100%, but we're still looking into that. So this is maybe the representation we have of what we want with the model. We have an imagery split in 540 meters squares, and what we want the model is to assign to each of them a probability that is a mine. So here on the top right, you have 95%. That means the model is pretty certain that this is a mine, while in the top left is 49%, which makes sense because you have kind of more green, is like a mine, is like the edge of the mine. So again, that's what we want the model to do. And then we need to decide the cutoff. Okay, anything above 90% is a mine, or 80%. That's something we will need to decide. So for Sentinel-2, as of November the 6th, when I recorded this video, maybe in a month that we have the presentation, I will have new results. From the 74% images we obtained, so notice that we're missing a quarter of the country, that we don't have predictions for this bi-week. The best model is our ResNet 50, and we tried DenseNet 121, BGG 16, and EfficientNet V7. So we have tried other architectures with a learning rate of 0.0001 and 30 epochs. We have tried other parameters. This is the best we have so far. And currently we did only the red, green, and blue bands. So it's basically a picture, and that's what we see. But with the random forest, it was working pretty well with the infrared band. So we are hoping to add them and see if it improves the model. So this is the ROC curve of the best model. So in the x-axis, I have the false positive rate, and in the y-axis, the true positive rate. The dream will be to have a model up here, which is 100% true positive rate and 0% false positive rate. Of course, that's hard to achieve. And what we have here is that as we start lowering the threshold, I detect more mines, but I also get more false positives. So at the end, it's a decision on where do I want to stand. Do I want more true positive, get more of the mines, but at the cost of getting more false positives? But at the end, I get an ROC with an area under the curve of 74%. For Sentinel-1, again, the best model as of November 6th, obtained with 88% locations. So notice that with Sentinel-1, we get more location. That's something you want. You want to be able to see under the clouds. And with these combinations of the band, the BB, DH, and RFDI. So we have tried other, and this is the best so far, but we will definitely keep trying before going to the testing data and releasing to the public. The unfortunate thing is that the area under the curve of the best model is lower. It's only 68%. And we are still trying to understand, because something I don't like, and you will see it later, is that most of the predictions are kind of like 0, 1. There is no much in the middle. So we don't get that much variation. That would be ideal to do the next step, which is a combination of the two models. So here I have a scatter plot of the probability that is currently predicted by Sentinel-1 and the probability that is currently predicted by Sentinel-2. So I think it's because the softmax function that we're getting too many zeros and too many ones, because if I will have more points in the middle, the combination of the models will do a better job, but this is what we currently have. So what we need to think is, okay, given the two votes of the image on Sentinel-1 and Sentinel-2, how do we aggregate? It would have been really bad if we will get all the points around the diagonal. That means that the models agree a lot on whether a point is a mine or not. So that will be useless to aggregate two models that they basically provide you with the same votes. But given that there is this much variation, there is a scope to do some aggregation with the two models. So remember, model of Sentinel-1, we had an area under the curve of 68% and 74% for the Sentinel-2 model. When we aggregate them, and we are currently aggregate them with this simple function, which is the arithmetic mean of the probabilities. So if one of them is missing, we just keep the probability of the model that is not missing. And if we can, we take the average. With doing that simple aggregation of the two models, I first increased coverage to 93%. So remember, with Sentinel-2, we only had 74%. With Sentinel-1, we got 88%. Now we increase it to 93%. So now we're able to have some prediction for 93% of the images. And we also improve the precision of the model. Now the area of the under the curve is 78% by combining the two probabilities of these two models. And this is how the ROC curve looks of this average model. The nice thing is, because you are kind of average a bunch of zeros and ones or number close to that, you at least get more points in the middle. And now the question is, politically, what do we want to report? Like maybe a true positive rate of 60%, so get 60% of the mines, but maybe that's a lot of mistakes, right? Because most of the country is not a mine. So then the false positive rates will be really intense. So what we're trying is to move this curve, make it more steep, so we get a higher true positive rate with a smaller false positive rate. Okay, enough with the machine learning part. Let's switch to the other part of the presentation, which is how do you translate this machine learning model, which was like the first part, into something that is used for policy. So what we did, with the help of SIG, like a company in the US, is to create this web page called COMIMO, Colombian Mining Monitoring, where we display our predictions, and then people can do different things. So I will try to show you some of the functionalities we have envisioned so far. So the first thing you can do is play with the municipality boundaries. If you don't care about all Colombia, you only care about your town, you can look here, or you can look at the map of legal mines, because the model only predicts mining activity, right, in red, and what you look in yellow is whether the mining activity is inside or outside a legal title. Then you can subscribe. So you basically, what you do is you put your email and you say, I want an alert every time you detect a possible mine in my jurisdiction. And what we want to be super upfront is that we will never get a model that is 100% precise. So what you get is an email like this, and we ask you, and we are upfront at saying there is potential mining activity in the area, and we ask you to take a look at the area here. And they go to Collect Earth Online, which will basically show you the following. This is the platform of SIG, where they are gonna get the GPS location of what the model thinks is a mine, and they will get high resolution image to do the validation. So to say it again, the model will never be 100% precise. It can be more precise. That's what we're working on. But we want to be upfront and saying this is a potential mine. Please go check yourself in this high resolution imagery. So thanks to the government of Norway, we are now obtaining for free for the tropics and image at a resolution of 3 meters. So people can go and check in their computers before going to the field, right? So they can say, oh yes, it is actually a mine, the model is correct, or it's not a mine, which will first help to create like a voting aggregation process. We can say to the authorities, look, we had this NGO and 4 citizens confirming that the model is correct. So actually just go act on this location. That is, it's not only that the model predictor is confirmed, but also it will help us to retrain the model in the future. One of the concerns is, what if the miners start reacting to the fact that you are discovering them from the satellite? Let's say, for example, they recognize that the model identified like this white footprint of the mine, so they start painting the mine with purple so that the model will not detect it. Given that the model will be constantly like receiving new imagery, once it starts noticing, oh, now the mines are purple, then the model in future iterations will be able to detect that. So that's, I guess, something important to keep the model updating. Another thing you can do in Comimo is to first look at the time series agreement. That is, maybe 2 weeks ago I didn't detect this as a mine because it was flooded or something else. So you might want to look for more agreement, not on the validation side, but on like the model through time. So you can look at the time series agreement, and you can do these advanced options. So just do receive emails, the validation, or do search, and of course there will be an option to download the data for like advanced users that they want to deal with the rasters or shapefiles behind the scenes. They can also do that. So what are the future steps? Improve the precision of the model. We still think the model is not good enough to release. I guess we're planning to do it a couple months ago, but the pandemic has affected all of us, and also the government is not even thinking about mining. They are like busy dealing with the pandemic. So we still have time to improve the precision of the model. So we are working, and I hope that in a month that you will see me live, I might have better news. Then we want to release the interface, the Comimo webpage, so that we get the action going on the field. And we believe that it's not only releasing a tool, but it's also building the capacity to use it. So we have scheduled a course with government and NGOs. So we want to like teach people how to use this and be aware that it's not 100% precise. And so we have been doing agreements with the National Police, with the National Prosecutor Office, with some environmental regional authorities. So we are working on that side because we want to, like, the technology is there, but if they don't use it, we are not going to see change in the world. And also, we plan to release Comimo and all the material of how to use the platform to the public. I imagine people commuting to work and they just want to do some validation around national parks, so they receive an email, and while they are holding the rail with one hand, they can be clicking yes or no is a mine. And that will definitely help if we have more users, and that will also help us a way of pressure, like, look, these many users have confirmed this is a mine, why haven't you act if the model was correct? So it will reduce detection time from like 2 years to like the couple hours once we process the image. And of course, it's not 100% precise, but with more users and with the government assigning somebody to validate the predictions, I think we get a faster response, and it's not going to happen anymore that when they get to the field, the miners are already gone. So thank you very much for your time. And